Hi, ladies and gentlemen. This is Mrs. Freeze, and today we're in Chapter 9, Lesson 2, talking about theoretical and experimental probability. Please have your composition book out and your math book out, so when it comes time to do some practice problems, you have your composition book and your math book ready for that. All right, at the top of page 722 in your math book, you have definitions for theoretical and experimental probability. Theoretical probability is just mathematically what should happen in a probability event. That's what your lesson was on Monday. Simple probability, okay, that was all theoretical probability. Experimental probability is what actually occurs during a probability event. In order to calculate experimental probability, it's very similar to theoretical probability. You still want to put the number of times the favorable outcome happened, the number of times what you wanted to have happen goes in the numerator, and the total number of outcomes goes in the denominator. Let's look at an example. Okay, at the top here, it says, what's the probability of rolling a 4 on a die? Okay, this is going to be our theoretical probability. They're asking us to find mathematically what's the probability of rolling a 4 on a die. Okay, well, we know on a die there is only one 4 out of the 6 numbers. 1 divided by 6 is 0.1 and 6 repeating, so I'm going to round that to 7, and that is a 17% chance of rolling a 4 on a die. Now, if you look right here, it says, what's the experimental probability? I'd like you to go ahead and make this table on your composition book. Okay, pause the video, make the table, and when you're ready, come back. Okay, so before we start our experiment and we actually roll a die, we need to list the possible outcomes on a die. We know we can roll a 1, a 2, a 3, a 4, a 5, or a 6 on a die. All right, let's get our die out. I'm going to move it over here so we can actually see what we're doing. I'm going to set my timer for a minute, and we're going to see how many times we actually roll a 4. All right, here we go. That's a 2, so we're just going to put a tally mark whenever we get one of our numbers. 3, 2, 5, a 3, a 1, a 5, no 4 yet, a 3, a 1, 3, yay, a 4. That's 5 when I put a slash like that. A 1, 3, another 4, another 4, yay. A 1, 3 is the winner here so far. 6, all right, time is up. Okay, now, the frequency just means how many times I rolled each of my numbers, okay? So we're going to write how many times we rolled each of the numbers here for our frequency. We rolled a 1 4 times. We rolled a 2 twice. 7 times we rolled a 3. 3 is the lucky number today. And we rolled a 4 3 times. We rolled a 5 3 times, and we rolled a 6 just 1 time. All right, so now we are able to calculate our experimental probability. First, we need to put how many times did we roll a 4? Remember favorable, what happened that you wanted to have happen? goes in the numerator. So 3 times we rolled a 4. The denominator is the number of possible outcomes, okay? Total number of rolls. So how many times did we roll? 6 plus 7 is 13. 13 plus 6 is 19, 20. So we rolled 20 times. Okay, so 3/20. Let's divide 3 by 20. 3 divided by 20 is 0.15, which is 15%. So experimentally, I was really close to what math said should happen when I try to roll a 4 on a die. Let's do an example. It says a number cube is rolled 25 times. It lands on 3 or 6, 5 times. Find the experimental. So this was were the results from the experiment, okay? And the favorable happened. It landed on a 3 or a 6 5 times. Out of the total number of rolls was 25. That is 1/5. I know when I do 1 divided by 5, that's 2/10. And that is a 20%. So 20% of the time when I rolled my die, it landed on a 3 or a 6 in my experiment. But theoretically, what should happen? What does math say should happen theoretically? Well, on a die, my favorable outcomes, there is 1 3 and 1 6. So 2 numbers could pop up out of the 6. That would be the favorable. When I simplify that, I get 1/3, and that is 33 hundredths or 33%. So mathematically it says 33% of the time I should land on a 3 or a 6. Then it also says compare. Okay, so I found my experimental, I found my theoretical. Compare means say what the difference is. So theoretically, math said, right, theoretically, I should have landed on a 3 or 6, 13% more times than I did, right? A lot of different ways to write the comparison, but that, then I did, I should say experimentally, right? So when it asks you to compare, you want to make a little statement there about the math that you found. Okay, you're going to have a problem like this on your homework. So number 3, on page 725 is like this problem right here. All right, it says the table shows the results of an experiment in which Alexa spun the spinner shown 20 times. So she spun this spinner 20 times and she landed on a 1 4 times, a 2 5 times, a 3 5 times, and a 4 6 times. Okay, these are her results. It says, what's the experimental probability of the spinner landing on 4? Okay, well, this shows on the table that 6 times out of the 20 total times that she spun, she landed on a 4. If I divide both of those by 2, excuse me, that's 3/10. And as a decimal, it looks like this. And as a percent, it is 30%. So experimentally, 30% of the time she landed on a 4. B says, what is the experimental probability of the spinner landing on 3? And then C says, what is the theoretical probability of the spinner landing on 3? And then compare. I would like you to pause the video and complete B and C. When you are ready for me to go over that with you, go ahead and push play. Okay, so the experimental probability of the spinner landing on 3, it landed on 3 5 out of the 20 times. That is 1/4, which is a 25/100ths as a decimal and 25% as a percent. What is theoretical probability of the spinner landing on 3? Well, theoretically, there's 1 3 on the spinner out of the 4 possible numbers it could land on. And that is also 25/100ths and 25%. So that's my theoretical probability. Then it says compare, and I have to say that theoretical and experimental probabilities of landing on 3 are equal. So just a little statement about the comparison. This time they are equal. So mathematically what it said happened actually did happen in the experiment. Okay, let's look at this problem. This is actually at the top of page 724, example 5. I've shortened it a little bit, but it's basically the same question. Last year, a DVD store sold 2,000 DVDs. 580 of the DVDs sold were comedy DVDs. If the store sells 5,000 DVDs this year, how many comedy DVDs can he expect to sell? Well, let's start with the rate that they actually sold out of the 2,000 that were comedy. Okay, so this is going to be total sold. Let's make our table. And over here, this is comedy. Starting with our rate. So he sold a total of 2,000 DVDs, but 580 of those were comedy. Now, you know, in order to find the COP, remember it's Y over X. So I'm going to divide 2,000 by 580. Remember, it's Y, and this is my X, and this is my Y. It's Y over X. So 2,000 divided by 580, that is I'm going to round it, 3.45. So 580 times 3.45, and that's a rounded number, gives me about 2,000. Okay, the question is, if the store sells 5,000 DVDs total this year, okay, if they sell 5,000 total this year, how many comedy DVDs can they expect to sell? Well, remember, if we multiply to get from X to Y, then we divide, and we always say by the reciprocal, but that's really, we multiply by the reciprocal to get back the other way, right? So we're going to go like this to get back over here. So that's going to be 5,000 divided by 3.45, And that gives me 1,449.27. So I'm just going to round that to 1,449. So that's how many DVDs he would sell as comedy DVDs if he sold a total of 5,000 based on this rate here. $1,449 comedy DVDs. All right. Please start your homework and let me know if you have any questions.